Okay, so this is a question from June 2006, paper 6, A23A. So it's question 2 from June 2006, module 6. Write down an equation for any one of the nuclear fusion reactions which is believed to occur in the Sun. So there's several nuclear reactions here that would be acceptable, but all of them really are hydrogen going to helium. So you could have, for instance, hydrogen 1,1 plus deuterium, which is hydrogen 1,2, and that then becomes helium 3,1, where we've got a balance here. Or you could have a hydrogen plus hydrogen coming together to form deuterium, and a positron being produced as a result. So either of those two reactions would have been acceptable. Next part of the question, state 2 advantages that fusion reactors would have over current fission reactors if they could be made to work successfully. Well, the first thing is that they don't produce any long-lived nuclear waste. So there's no long-lived radioactive waste, and I think it's important to identify there that it's radioactive waste that you're concerned about. So there's no long-lived radioactive waste. That's the first part. And secondly, the fuel that's required for it is an almost limitless supply. So we have an almost limitless supply of fuel, and that comes from seawater. Okay, so with the two advantages there over nuclear fission. Nuclear fission produces long-lived radioactive waste. There is some radioactive waste produced in a fusion reactor, but it's not very long-lived, not nearly as long as it is from the byproducts of nuclear fission, and it has a limitless supply of fuel in the form of seawater. Then name any two methods of plasma confinement. Well, we could have inertial confinement, we can have magnetic confinement, or we could have gravitational confinement. And gravitational confinement is what happens on the Sun, on the Sun and stars. Okay, so we therefore have three choices that we could have for that confinement. Then to overcome proton-proton repulsion, nuclei need energies of the order of 110 kiloelectron volts, and we're asked to use this value to estimate the temperature needed for a proton to have this amount of thermal energy so it will work in light. Well, here what we're assuming is that the energy of the proton is similar in nature to the energy possessed by a gas molecular atom when it has kinetic energy. So what we're saying is that the energy of the proton is going to be equal to 3/2 kT. That's a half mc squared brackets equals 3/2 kT in kinetic energy, in the kinetic theory for gas molecules. We're assuming that the proton has the same. So that means then 110 times 10 to the power of 3 is equal to 3/2 times, and K has a value of 1.38 times 10 to the minus 23 times then the temperature. When we fill in those values, that gives us a temperature which comes out at about 8.5 times 10 to the power of 8 Kelvin. So 8.5 times 10 to the power of 8 Kelvin, and that's a good idea to remember that kind of temperature in case in a future question they asked you for an estimate of the temperature required for nuclear fusion.